single bit adder. Now what could be the other thing? So if we want to extend this particular idea, then you see, let's say I want to add 64 bit numbers. Okay, so what does that mean? It means that if I'm using single bit or one bit full adder, how many cycles it will take? 64 cycles. So let's try to see that if I am taking I'm using single bit full adder, I'm taking 64 cycles, what is the overall latency? Let us say my one bit adder is determining this is the critical path. If this is the critical path, what would be the overall latency of one addition? Overall latency of the addition would be defined by 64 into delay because of one full adder plus setup time of register plus delay of a register, latency of a register. So because of latency of the register itself, the when we see the overall latency of 64 bit addition here, that part could be dominating. Okay, it would be non-negligible, it could be significant part of my latency. So the advantage what we were trying to get from dividing things into very smaller pieces may not be there. So that's why it could be the other these things are more practical. So if we use, instead of 1 bit adder, we use 16 bit adder or a 32 bit adder. So for example, if we are using 16 bit adder, then it would take 4 cycles. We'll first add first 16 bit, then next 16 bit, then next 16 bit. So this way it will take 4 cycles, and if we are using 32 bit adder, then it will take 2 cycles. So addition using this 32 bit and 16 bit adder is more practical, because there the fraction of time which is used by register is also less, and the advantage, whatever advantage we want to get because of reduction in clock period, can also be obtained. The other the other benefit because of that could be that we can design a pipeline design. What is this pipeline? So let's try to understand what is this pipeline. So when we would do this pipeline design, whatever it is, so whenever we do this pipeline design, we would be able to reduce the clock cycle, but may also have the same throughput. So what is this throughput? That also we'll try to understand in next couple of slides. So the overall message here is that we would be able to reduce the clock frequency because the size of my addition is less. Along with that, performance may not be impacted. So let's say my 32 bit addition is done using 2 cycles, but still how good it would be that if my result is still available after every cycle. So that means I am able to reduce the clock frequency by half, and also I am able to get my output every cycle. So that means overall effectively I have reduced my delay by half. Okay, so let's see with the example of this 32 bit adder, and if we would like to do 32 bit adder, 64 bit adder using 64 bit addition using 32 bit adder, let us see how we go about it. So since I said, so basically if we would like to add 64 bit numbers, but the adder which we have available is only 132 bit adder. So what we can do is we can divide the whole number into 2 chunks, first 32 bits and second part of the 32 bits. So let's say A and B are 2 numbers, and we can say that first 32 bit is 0 to 31 and the second part is 32 to 63. So similarly, B can also be divided into 2 parts. So although it is available as a register, so either, now there are 2 possibilities here. If it is a 64 bit register, now there has to be a mechanism so that out of the 64 bit register I can read either this part of upper half of the register as well as the lower half of the register, or what we can do is this A could be a mix of 2 registers which are 2 32 bit registers, so that these 2 different parts could be read individually. So both are equal possibilities, and in practically also both are feasible. So having one 64-bit register and reading two different parts of the 64-bit registers is also equally appealing as well as equally possible than having two 32-bit registers and considering them as one 64-bit register. Okay, so somehow I have to provide a mechanism so that only either the upper part or the lower part will be added, will be given as an input to my 32-bit adder. So I have put a mux here. So this mux, there would be one select line. With this select line will say that whether upper half or lower half. Sorry, this is the lower half, this is the upper half. So whether upper half or whether the lower half, which one should be selected. So there would be two muxes here, and similarly at the output, because there is only 32-bit output, so that output has to go to a S register, which is again a 64-bit register. So here we have to say that there is a demux here, demultiplexer. So this demultiplexer will decide whether the upper part or whether the lower part of this this sum, this S register would be written. So now because we have to find which part would be written, so there would be a demux here. So if demux means that whether this upper part or the lower part, and we also have to select in the S accordingly that which part to be written. Okay, so since after first addition my Cout has to go to as a Cin of the second half of the addition, so this D flip-flop is still required. Okay, what about the control? Control would be here we can say that we would have two states, let's say S0 state and S1 state. So whenever we are there in S0 state, then upper half so this lower half would be selected, A30 0 to 31, B0 to 31 would be selected, and the output would be given to S0 to 31. Okay, so when S1 is there, then we will enable the second part. So this the second input of the mux would be selected and the second output of the demux would be selected. So after second state we can also make this clear the D flip-flop, so that can also be done. So yeah, so this is one particular type of design where this addition is done using two clock cycles. So if we say what is the clock period? Clock period would be the delay of 32-bit adder plus T setup time plus T reg time. Now if we compare the latency of this 64-bit addition, latency means let's say this 32-bit adder is in the critical path, then what would be the latency? Latency would be twice the delay of 32-bit adder plus twice setup time plus twice the register time. So let's say if these two are negligible in comparison to delay of 32-bit adder, then we can say that the latency is essentially twice the 32-bit adder delay. And if we would like to compare this particular design with the ripple carry design of my 64-bit addition, then we can say that this design is almost as good as 64-bit ripple carry adder with half the area. Okay, so my area is reduced to half because I'm using only 32-bit adder, not the 64-bit adder. So area would be clearly the half, and my delay is almost the same. So this is a very good design trade-off, that if we would like to reduce the adder area by within the same cost, then the sequential design, which is a multiple cycle design, could be quite effective. Now let us see the another trade-off point. So let us try to use 64 or basically two instances of 32-bit adder, and this is the alternate design. So here no muxes are used, no multiplexers are used, but the design is something very similar. So we are using two 32-bit adders, only there is no mux here, so that means only the lower half of A and B would be added here, and upper half of A and B would be added in the second adder. Okay, so the output here, we have to understand that it's again a clock design. So basically in cycle 0 this is being performed, in cycle 1 this is being performed. So the result here would be stored in S, lower half of the S. Here result would be stored in the upper half of the S. So the output here is stored using D flip flop, and it would be available to this second adder for rest half of the cycle. Okay. So if we see this kind of a design, then you will say, what is the benefit? Effectively the area is same as 64-bit ripple carry adder with the addition of one flip flop. These registers, we assume that it would be still required in both the cases. The other interesting observation here is that my adder, first adder, this adder is free, is occupied in 0th cycle, and this is free in the 0th cycle, and in the first cycle this adder is free and this is occupied. So only one adder is working at one point of time. Okay. So is it an advantage? It looks like it's a disadvantage, that we have some resources but they're laying idle. There is no utilization of that resource. How can we say that this is an advantage? So to make this thing into an advantage, what we can do is that as soon as the first addition is done, first part of the addition is done, we can use this 32-bit adder to add some other number if they are there. So if we want to add some other number, then this 32-bit adder, first adder, can be used to add that number, and in the next clock cycle it can give the result here. So this carry out would be used here, and then we can the second part of that computation could be done. I can understand it's not clear, so let's try to understand it with an example. So let's say I want to add these 5 numbers: S equal to A plus B plus C plus D plus E. Now because we have adder which take only 2 inputs, so this addition can also be written as S equal to A plus B, then S equal to S plus C, then S equal to S plus D, then S equal to S plus E. So some of you may question that why we are not using a tree. So if we are using tree addition, then it would require multiple adder, but let's say for currently we have only one adder which is there with us, only single adder is there, so then we would be able to do it in 4 different steps. Okay. So when we are doing things in 4 different steps, so let us say what would happen. Let's say we have these adder 1 and adder 2, they are represented here, and now in cycle 0, T0, A and B, lower half of A and B is added. Okay. Now in cycle number 1, upper half of A and B is added. So by the, this is T1, not T2, this is T1. So in this T1 this is added, and along with that, because we said it is this particular adder 1 is free, this adder 1 is free, so here what we can do is we can start computing S plus C. So you see that at the end of this clock cycle my S 0 to 31 is ready. It can be used. It can be because it is saved in a register, so it is available to be used. So S 0 to 31 is available, and we also start adding the C number, lower half of the C number. Now in the next cycle, this computation, the second part of this computation would be done. So when we are doing the second part of the computation, S 32 to 63 would be given as a input, and the upper half of the C would be given as a input. So you see, by the end, this 32 to 64, 32 to 63 will also be available, so which could be used in this T3 cycle. Okay, so now again my adder 1 is free. Because adder 1 is free and I have already computed S0 to 31, so what I can do is I can start doing the third addition. So when I start doing the third addition, then I'll take the lower half of the D and also the lower half of my S, and then in the next clock cycle, by the next clock cycle, so this result would be available. Okay, and because this result is available, now adder 1 is again free, so we can start the fourth addition, which is S plus E. So lower half of this fourth addition we have started. Now by the time T5 will come, this computation would be done. So how much time this whole computation has taken? How much time this whole computation has taken? 5 clock periods. So there were 4 additions which were done, and total amount of time taken was 5 clock cycles. So can we say that one addition is done on an average in 1 clock cycle? This is what we call throughput. So if we have n number of tasks, how much amount of time we take to do n tasks is called throughput. So let's take a quick analogy. So let's say you were given 5 different assignments, one for digital logic design, one for computer architecture, one for mathematics, one for electronics. So let's say 4 different assignments, and everything was given 1 week of time. So one possibility is that you are doing all of them one by one and then finishing it off. The other thing could be that because you were spending some time parallelly, whenever your brain was free, or when you have put your computer on work and some simulation was going on, till the time your computer was busy, your computer was doing some computation, by the time you are doing some writing job. So this kind of thing is called parallelism. So this way, because or multitasking, so your mind is one, but it is doing multiple tasks at same time. Although you can take now, if you are able to finish all these 4 assignments in 4 days, so that means the overall latency is going to be 4, but throughput is going to be, on an average, you are saying that you have finished 1 assignment per day. Correct. So this throughput is also an important measure for performance, and here we clearly see that throughput for such kind of an adders are quite good. This is called pipelining. Okay, this is quite a popular process in industry, more in the manufacturing. So they call it pipelining. So basically, let's say you're manufacturing car, so one person would be designing tire, another would be designing chassis, another would be designing body. So as soon as one is done, he'll pass it on to other, then whenever second is done, he'll pass it on to other. So this way this kind of a pipelining goes there. Now this pipelining is quite a generic, and we see in our daily life also. So for example, when you go to a Golgappe wala, then also he will give it to one, then he'll give it to second, then he'll give it to third. So by the time one will finish, then he'll give it again. So this is a very generic concept, could be applicable in many real life applications, and also applicable in many of the digital design circuits also. So it is more applicable when the design is multi-cycle. So if it is multiple cycle, then you can say that in one cycle we do this, in the second cycle we do this, and then we can by the time second cycle is done, some new operand can come and can start operating. Okay, the only condition here is, or the best possibility when pipelining will give best benefit, when all the tasks are equal in terms of time. So here this addition and this addition both were taking same amount of time, so it was almost perfect that the total throughput is 1 cycle and total latency is also almost the double, but throughput is actually the throughput is also double. So basically we are able to perform one task in 1 cycle or one addition in 1 cycle. Okay, so with this I would like to close today's lecture. So in today's lecture we have seen couple of new interesting concepts. So one thing we have seen that how sequential circuits can be used in other applications like additions. Now addition we have done as a combinational design. Today we have seen the same addition in a sequential design, and when we did that in a sequential design, it become a multiple cycle design. And in this multiple cycle design we also have to design our own state machine, where we clearly define that what would be done in state 0, state 1, state 2, state 3, etc. And also we have seen that how pipelining could be quite an effective in digital circuits, where it can help us in increasing the performance by increasing the throughput while keeping the latency almost the same. With this I would like to close. Thank you very much.